Ever wondered how social networks, transportation systems, or web page rankings work? They all use a concept known as graphs in their data structures. Now, these aren't the bar or pie charts you're probably thinking of. In computer science, a graph is a fundamental data structure used to represent connections and relationships. This is the basis for social networks like Facebook, transportation maps like the London Underground, and even the algorithm Google uses to rank web pages. These graphs consist of vertices or nodes and edges. Vertices can be anything from cities, people, or web pages. The edges are the connections between these vertices. They can be one-way, two-way, weighted or unweighted, representing different types of relationships. Understanding graphs and their properties can open the door to efficiently solving a wide range of problems. So, ready to dive into the world of graphs? Here we go! A graph comprises of vertices and edges. But what do these terms mean? Let's break it down. A vertex, sometimes called a node or a point, is essentially an element in a graph. Think of it as a standalone entity that holds a position within the graph. These vertices can embody a multitude of things. For example, in a transportation network, each city would be a vertex, or in a social network, each person would be a vertex. Now, these vertices don't just float in space. They are connected by what we call edges, also known as links or arcs. An edge is a line that establishes a relationship between two vertices. For instance, in our transportation network example, the road between two cities would be an edge. In a social network, a friendship or a follow would be an edge. Edges can have different characteristics. Some are directed, meaning they point from one vertex to another, signifying a one-way relationship. Others are undirected, implying a two-way relationship. There are also weighted edges, which have a numerical value associated with them, representing something like distance or cost. Let's go back to our transportation network. A directed edge could symbolize a one-way street between two cities, while an undirected edge could represent a two-way road. A weighted edge could denote the distance or the cost of the journey between these cities. In a nutshell, a graph is a collection of vertices, each connected by edges. It's a simple concept, but its flexibility allows it to represent a vast array of real-world scenarios. From modeling social interactions to mapping out the world's transportation systems, graphs provide us with a powerful tool to represent and analyze complex networks. So remember, vertices are the entities, and edges are the connections between these entities. Understanding these components and how they interact is the first step in unlocking the potential of graphs. Not all graphs are created equal. There are different types of graphs. So let's dive into the world of graphs. First off, we have directed graphs, also known as digraphs. In a directed graph, the edges or connections have a specific direction. Picture a one-way street where traffic only flows in one direction. That's what a directed graph is all about. It's a one-way connection between two vertices. On the other hand, we have undirected graphs. Unlike directed graphs, the connections here are bidirectional. Think of it as a two-way street where traffic can flow in both directions. An edge in an undirected graph signifies a two-way connection between vertices. Then we have weighted graphs. These are a step up from the previous types. In a weighted graph, each edge comes with a numerical value, or weight. This weight can represent a variety of things, depending on the context. It could be the cost of a transaction, the distance between two cities, or any other attribute of the connection. Next on our list is the directed acyclic graph, often shortened to DAG. This is a special type of directed graph that doesn't allow for cycles. In other words, there's no sequence of edges that forms a closed loop. It's like a hike where you can't backtrack on the path you've taken. Lastly, we have trees. A tree is a unique type of undirected graph. It has no cycles, and there's exactly one path between any pair of vertices. It's like a family tree, where each person can trace a single lineage back to their ancestors. Understanding these types of graphs will help you choose the right one for your specific problem. Remember, each type of graph has its own strengths and weaknesses, and is suited to different kinds of problems. By understanding the distinct features of each type, you can select the most appropriate graph for your data and make your analysis more effective. So the next time you're faced with a data problem, think about the type of graph that would best represent your data. It's all about using the right tool for the job. To work with graphs, you need to know how to perform certain operations. Let's kick off with the basics. Adding a vertex. This operation is as simple as it sounds. You're essentially introducing a new node or point into the graph. This could represent any entity of interest, from a new user in a social network, a new stop in a transportation network, or a new web page in the World Wide Web. Then there's the operation of adding an edge. This is about creating a connection between two existing vertices. Just imagine you're drawing a line between two dots. This line could represent a friendship in a social network, a road in a transportation network, or a hyperlink in the World Wide Web. Now, what about when you need to remove elements from your graph? The operation of removing a vertex involves deleting a node and all the edges connected to it. It's like erasing a dot and all the lines connected to it. This could be due to a user leaving a social network, a stop being closed in a transportation network, or a web page being taken down from the internet. Removing an edge, on the other hand, involves eliminating a connection between two vertices. It's like erasing a line between two dots. This could be due to two users ending their friendship on a social network, a road closure in a transportation network, or a hyperlink being removed from a web page. Last but not least, we have traversal. This operation is about visiting each vertex in the graph in a systematic way. It's like going on a sightseeing tour where you visit every single point of interest. This comes in handy when you need to explore all users in a social network, all stops in a transportation network, or all web pages in the World Wide Web. And there you have it. Adding vertices and edges, removing vertices and edges, and traversal. These operations form the backbone of working with graphs. They're not just theoretical concepts, but practical tools you'll use time and time again when dealing with graphs in real-world scenarios. Mastering these operations will allow you to manipulate graphs according to your needs. Now that you understand graphs and their operations, let's see how they are used in the real world. Graphs are not just abstract mathematical structures. They are applied in various scenarios to solve complex problems. For instance, social networks are a prime example of where graphs come to play. Here, each user is considered a vertex, and the connections or relationships between them are represented as edges. This helps to analyze the network dynamics, find influences, or predict trends. Transportation networks also heavily utilize graphs. Think of cities as vertices and routes between them as edges. This can be a roadmap, air traffic routes, or public transportation systems. Graphs make it possible to find the shortest or most efficient path from one location to another, a fundamental problem in logistics and navigation. Next up, computer networks. Here, vertices represent devices such as computers, routers or servers, and edges represent the connections between them. Graphs help in optimizing network design, analyzing network performance, and detecting potential vulnerabilities. Web page ranking is another interesting application. Algorithms like Google's PageRank use graphs where web pages are vertices and hyperlinks between them are edges. By analyzing these graphs, the algorithm determines the importance of a web page, contributing to its ranking in search results. Finally, graphs are crucial in scheduling and planning. This could involve project management, job scheduling, or resource allocation. In this case, vertices represent tasks or events, and edges represent dependencies or constraints between tasks. Graphs help in finding the most efficient sequence of tasks, avoiding conflicts, and optimizing resource usage. The versatility of graphs is what makes them a powerful tool in many fields. Whether it's social science, computer science, logistics, or even search engine optimization, graphs provide a flexible and efficient way to represent and analyze complex relationships. Understanding graphs and their properties is not just for mathematicians or computer scientists. It's a vital skill for anyone working with complex interconnected data. Graphs, with their vertices and edges, are more than just a mathematical concept. These intricate data structures are the underlying foundation of our interconnected world. From representing relationships between individuals on social networks, mapping out transportation routes, to structuring computer networks, and even determining web page rankings, graphs are truly versatile. They come in various forms: directed, undirected, weighted, acyclic, and even as trees. Each type has its unique characteristics and uses. And with operations like adding or removing vertices and edges, or traversing through the graph, we gain the ability to manipulate and explore these structures. Mastering graphs opens up a world of problem-solving opportunities. It's an essential skill set for data analysts and anyone dealing with complex systems. So the next time you use a social network, remember the graph that's working behind the scenes.